So my name is Michele Gregorini, as I was introduced, and I am the CEO and founder of Diagnostics. Today I will be talking about how we build automated PCR systems, which we call, let's say, point of care or point of need platforms, which are optimized for emerging pathogen detection. The problem we want to solve, or the problem we are addressing, is the long lead time and the complex procedure that today the user has to go through before he can get an actionable answer from the moment when he suspects a disease or from the moment when he wants to diagnose a virus or bacteria. So you have to take the sample, ship it, then the sample is transported to a laboratory, then they have to do some preparation, they need laboratory technicians to handle the sample, run it on machines, and machines are usually considerably expensive or definitely not a simple piece of equipment. Then you need to interpret the results, and sometimes this is a big topic per se. How do you judge between positive and negative? The machine doesn't always give you the right answer, and I will go back to this topic later. Well, it gives you an answer, but doesn't always tell you positive or negative. And then you communicate back the results, and finally you have an action. And the whole process takes a long time, days, and it costs quite some money. We all remember the workflow during COVID, now 5, 6, 7 years ago, but it's still the same today when you want to get a reliable answer. Of course, you can go for point of need solutions like rapid test. However, the accuracy there is very low and it's hard to trust them. Maybe they give you an indication if you are really in desperate needs, but usually they're never really used for final answers and for accurate results. So our goal in our company has been to develop a point of need solution, a platform that allows you to have the best accuracy, so the same that you get in an external laboratory, in a short time. We are talking about 30 to 60 minutes and at very low price per test. We aim at being a few dollars per test, a few francs per test. The idea is that with our platform, the user can load the sample with minimum hands-on operation, and in the order of a few seconds per sample, press the button, and in less than 1 hour, you have not only the results, but also the complete results. So the positive, negative, you can immediately take an action. You don't just get the curve or some number, but you get positive, negative results. The platform, well, there are several platforms on the market, similar or that go in a similar direction. However, we try to have this advantage of being a closed system that works in combination with our unique cartridge. And this is an advantage because we can customize the system, as you can imagine, an espresso machine, so that every cartridge can be tuned for a specific disease with many combinations possible. We can even load multiple targets on the same cartridge and, for example, screen for up to 20 or even 40 possible different applications with one go with one cartridge. And you can imagine the cost of the consumables is basically the same, no matter what target what disease we are targeting. So you can achieve a very low cost per test or cost per target because of this intrinsic multiplexing capability. What makes us also special is that the cartridge is stable at room temperature, so you don't need any cold chain for transportation and storage. And we have done several rounds of tests in remote countries. My colleague Toby will tell you more about that later, where we could really show that you basically ship and forget. You send the cartridge, they stay on the floor for 2 months at 70% humidity, 30 degrees. And when you take them out of the pouch, they just work just fine. This is a great advantage because cold chain, the whole cold chain is a huge topic. It was a huge topic during COVID, we all remember, and in general, it's always a delicate step. You can have cold chain during transportation, but then you can have a period at the airport where your cargo is under the sun for some time, and you don't know how much the temperature increases in that case. Being 100% room temperature is a considerable advantage, especially for resource limited settings. The cartridge works on our closed system, on our platform, which is a small device the size of a microwave, just to give you an idea. And basically the workflow that we offer, the user has just to load these 3 cartridges that you see here, the one I presented you just earlier, and an additional cartridge to perform DNA and RNA extraction, also stable at room temperature and with the same feature. So once you load the cartridges, you run the machine. The machine will know what program you're testing for, and at the end, it will give you the results directly on the screen. So really, there is some hands-on operation. You still have to load the sample. It's not meant to be 100% lay user ready. We still target a person that can at least load the sample into the machine. However, the workflow is significantly simpler compared to any other machine on the market, where you not only have to load the sample, but you also need to know what chemicals you have to load. The chemicals have to be stored in certain conditions. You need to calculate concentrations. All of that is taken care of. Okay, so as I mentioned earlier, we have not a long history, but we have some history of development of machines. The first version that you see in these pictures had this nice pyramid shape, and we had the opportunity to test it in many settings in several countries around the world. Toby will mention more later. And thanks to these experiences, we had the opportunity to understand what the requirements are when you are outside of your comfort zone, outside of your lab, what issues you can encounter that maybe in the design phase you don't even imagine, because you focus on the technical aspects of the machine, you make sure that all the specs are met, but you maybe struggle to realize that the customer will not use the machine in the way you think, will do things that you can't foresee at the beginning. So all these real world feedback can be gained only if you go out and test. And we had the opportunity to do a bit of that at the beginning, and we obviously always do that as the product evolves in time. We always try to reach out and get as much feedback as possible. So what can go wrong? And today I would like to share with you some of our learnings. So what are the main issues that you have when you go outside of your lab or outside of your production space? Well, there are, of course, many possible failure modes, and I just list a few that for us were probably the biggest findings. First, never underestimate transportation and handling. This is maybe obvious, and there are also obviously standards that that basically tell you how to test for transportation, for vibrations, for handling, but the temptation is always to underestimate how complex and how harsh transportation can be to your equipment. We had many cases of machines working perfectly fine. We did our shaking test, our vibration test in-house, and then when you ship them, you don't know what happens. They go upside down, they undergo strong acceleration, strong vibrations, and all of a sudden something breaks. Even small things like screw, because of the vibrations, screw will come out. Of course, you use thread lock, you use protections for that, but nevertheless, there is always some components that fails in a way that you struggle to foresee at the beginning. So learning number one is don't underestimate transportation. It's a topic per se, and you need to have dedicated testing and dedicated design considerations for transportation. Second, and also hard to predict sometimes, the power outlet or the electricity requirements that you have in your lab, in your facilities, are hardly the same as what the customer has in a remote country. Even within the same country, sometimes we experience differences or fluctuations, And when you go overseas or into another continent, there can be significant instabilities in the power line, significant differences, although the nominal values are maybe on paper the same, but you have maybe big fluctuations, power spikes, and all of this can damage your equipment. And can damage, if you're lucky, you can see that it reboots or something happens, and if you're not lucky, you don't even realize that there is a damage happening, and you maybe take some time before you actually see the consequences. Again, this is not a new science, it's well known, and there are standards and tests just for power and for fluctuations and for emissions. And of course, you do all these tests before you send out. However, there is always surprises. The test doesn't have a 100% coverage. It's very difficult to foresee all the possible scenarios, and something always happens. Something can always happen where a fluctuation or a spike in the voltage causes a behavior of the machine that you don't expect, that you don't know. For us, this was an issue, and it's still sometimes it bothers us to think what could go wrong, what power fluctuations we could have. And it is important that, of course, you follow the standard, you test in-house, but again, you need to go out, distribute your machine, and see what happens when it's out there. And third, the operator skill, the person using the machine, is obviously always a delicate topic. As I mentioned at the beginning, our device is meant to be used, or let's say you need very minimal training to use our machine and also very few operations. So we believe, and we have always believed, that anybody could run it with a few minutes of introduction and training. But then there are 1 million ways, that the 1 million possibilities for the user to interact with the machine and maybe click or do things that you don't even imagine when you are building it. So the front end and the way you present your device to the user, the workflow that you offer to the user, is critical to make sure that they don't get completely unexpected results. Sometimes it's very hard to predict all the possible combinations, and there can be that combination that produces some results which look correct on paper, but are completely wrong, and they come out of a very weird operation procedure that the user took and that you could not even foresee when you were building the machine. So again, you learn this only by observing the customer, by sending it out and listening to what they complain about, what happens. And there is not an easy solution there. Of course, when you design the machine, you try to think about everything, but the only real feedback comes from the field. These are the, let's say, 3 major failure mode that we have when we talk about the device. And then there is a whole chapter of what can go wrong when you talk about the samples that the people will load. Of course, we have some specifications on what can be the input on our cartridge, but then even within the same types of samples, there are huge fluctuations in terms of matrix, in terms of content of inhibitors, in terms of how the quality of the sample in general. And maybe Toby will tell you more about that in a second. So how do we mitigate these, and what can we do to solve these issues? Well, of course, as I mentioned earlier, you can try to design your machine to the best of your capabilities and make it as simple as possible, but again, as strong as possible, as robust as possible. And then it's all about testing and gaining real-world experience. I just give you a couple of examples. In our machine, we have a very modular design where every module is meant to be replaceable. And for every module, of course, you analyze all the possible failure modes and all the possible requirements for the user. Does it need to calibrate? Is there wear? Is there failure? What will go wrong? What will break first? You do extensive stress tests in-house to be sure, or let's say also aging studies, to be sure that you know what will fail, when, and you try already to have either a solution in the best case, or at least an alarm or a flag that can tell the user that this particular component is about to fail. You also have to, as I mentioned earlier, test your machine. We did a lot of drop tests. This, again, is nothing new. It's regulated in standards. However, the standard sets some limits but you want to be sure you're well above the limits and your machines are much more robust than what they should be, because you don't want that the customer receives the product, takes it out of the box, and all of a sudden there is a component broken or something visually defective. So of course you start from the standard, and on top of the standard you build your own procedures to do the stress tests that you think are necessary and that you think will make you sleep fine at night, knowing that your machine will reach the customer in one piece. So we have a let's say we have built over time a chain of quality control procedures that allow us to be sure that when the customer receives the machine, it will work from the beginning to end and it will produce meaningful results. This is probably the biggest challenge, is to know, will the machine will maybe reach the end of the test and it will say something, right? But was there any fluctuation in environmental conditions? Was there any power fluctuation that somehow could affect my results? At the end of the day, you want to be sure that what your machine says is 100% correct, or at least you shouldn't say anything. The last thing you want is to say something that is not correct, right? Because then you would giving out false information. And the way to mitigate this, or the way to achieve this, in our eyes, is a level of QC, let's say a hierarchy of QC, where you start in the production, and then you have online QC, where you constantly monitor the deviations in the machine, intra-test and inter-test. So you have some thresholds and you check if the machine is always up to specs. And then you have, on the chemistry side, positive, negative controls on the cartridges to give you the ultimate answer whether the whole platform plus cartridge is actually giving out some meaningful results. I will now conclude. I will be happy to answer your questions. Of course, there is many more topics to cover, but I believe.
Thanks again for the nice introduction. Thanks for the opportunity to talk about what we do here at Diagso. The title of my presentation is Designing Molecular Workflows that hold up under variable sample types, operator skill levels, and field conditions. Okay, here we are. Okay, maybe I need the pointer. Yes, okay. So when we talk about reliable and reproducible molecular diagnostics in the field, we can also ask the question, why do molecular workflows fail in the real world? For those of you who are in the lab, who design assays, who run assays, who are involved in research and development, you all know that you can achieve pretty amazing results and efficiencies in a lab setting. I have an example here from one of our R&D projects where we look at the development of a new assay, where we have beautiful linearity of our assay across a wide range of different concentrations of a certain pathogen. Everything looks good. However, that usually is not how it ends up in the field, because in the field we have to deal with conditions and variables which we cannot control in the lab, and this is actually the challenge. So it can be like people who run the tests can be frustrated, they can be overwhelmed, they can be confused, they can misunderstand instructions. That all can lead to a failure in diagnostics. There are also topics such as shipments of samples. I mean, Michele talked a little bit about the shipment of the devices. It's the same with the cartridges. It can also be with samples collected in the field. This is actually a picture we received this week from one of our partners who wanted to run some tests. This is how the samples arrived in their lab. So that is the reality, right? And the next few minutes, I plan to talk about how we try to bridge that gap from excellent results in the lab to then make it work in the real world. I splitted this topic into 3 design principles, how at Diagso we try to deal with that. And the first one is actually just a follow-up on what Michele showed. It's basically what we do at Diagso with our fully automatized and ready-to-use platform for the entire molecular diagnostic workflow. So from extraction of nucleic acids, DNA, RNA, to the pipetting step, to the PCR, and then the data analysis, which is all automatized and combined in a single device. And so one of our approaches is that we minimize the number of manual steps. We try to reduce or avoid many pipetting events. As Michele mentioned, there is a single pipetting event on our platform where the operator has to load the sample into the extraction cartridge. Then we also avoid completely timed interventions, so there are no steps where the operator has to wait, because that introduces a lot of variability. And very important, and especially when it comes to the interpretation of the data, we try to get completely rid of a subjective judgment and just provide the end user with a final result. We use workflow features such as like pre-filled reagents. Michele showed you the pod. We do the same for extraction cartridges. These are closed cartridges where you don't have to add any additional reagents. Everything comes pre-filled and ready to use. And we also try to have, especially on the device, a guided workflow where the user basically clicks him or herself through the entire process and get some guidance. So that also helps to prevent mistakes. That's basically what we do with Diagso Care. Again, as also shown by Michele, this is our platform, which combines nucleic acid extraction with PCR in a single device. The second design principle is that we build technology for field conditions, and this from day one. And here, very important, what we consider is from the very beginning that we have a very high variability when it comes to biological material. This can include different matrices, but also things like the viscosity of samples can be different. If you think, for example, about saliva from patient to patient, this can be quite different. Also, as mentioned before, inhibitors are obviously a big topic when you do PCR, the pathogen distribution, the concentration, the biomass in general, which can all impact your diagnostic performance. We also have in mind that not all the operators have the same level of skills, so there can be differences when it comes to pipetting accuracy. Even if it's a single step, even if it includes rather large volumes, there are still differences. There is timing. Certain people are faster in loading a cartridge than others. The level of how clean a place is, a lab is, and how people are trained to prevent contaminations are also very, very different from place to place. And also when it comes to the interpretation of results, that obviously can also have quite some impact on the final result. What we also see, and that was nicely covered by Michele, is that the field has its own conditions, challenges such as temperature, humidity, and power. That affects, obviously, in the first place, the device itself, but also the consumables, also the tests, also control samples we send. That all has an impact. How do we do this or how do we deal with these challenges at Diagso? And one thing which we learned in the past years is that there's a huge advantage if you, first of all, start very early on in running your tests in the sites or in the trial sites where you finally want to deploy your technology. That's the first thing. And also if you run it at the same time in multiple sites. And I have here an example of a project we finished a few years ago. It was basically a collaboration between the Leiden University Medical Center in the Netherlands, which is a very nice and big institution, and then also with the Manisa Health Research Center in Mozambique, which is also a very nice institution, but obviously located in a completely different geographical region. And together with these two partners, we developed a cartridge for the detection of 3 different helminth species, including Trichuris, Ascaris, and Strongyloides. And the reason why I show it here as an example is we actually included all partners very early on into the design and then did the validation immediately at both sites at the same time, right? To early on identify any issues which might arise from having completely different environmental conditions between Mozambique and, I would say, the European Union. In the end, that worked out very nicely. We had excellent results in both sides. We also couldn't see any difference between Leiden and Mozambique. The data is published, and for those of you who are interested, I welcome you to look at the paper. I think the colleagues in Mozambique and in Leiden did an excellent job. Again, this is an example for how it can help to do or to build the technology for the field conditions from day one on. The third design principle I would like to quickly touch is, I believe, the most important one, and that's make sure that the technology, as good it might be, is nicely integrated in existing workflows. And here, obviously the effectiveness of your technology, and again, that might look very nice in the lab and it might be the most beautiful assay you can come up, as long as it's not integrated in an existing workflow, the likelihood that it fails is pretty high. So we had to learn that, obviously, the hard way. So the first thing is always we try to understand what systems are in place, how do they work, and I will come later to, I will also show you some example, a positive one, a negative one, what this actually means. Very, very important, know who you're working for, who do you design the technology for. That includes obviously the operators, but also decision makers, right? Logistics, I think we touched that very extensively, also with Michele's presentation, that needs to be integrated from the very beginning. And then another point is costs, right? So it needs to fit into existing workflows. And then also a topic which becomes more and more important is data integration, and that is 2 parts, I would say. One is like the literal integration of data into existing, like laboratory management information systems, also, as well as also, I mean, who has ownership on data security, also dealing with IT, which we also learned is probably also something you don't think about it, but I mean, if you have devices as we have, which can be nicely integrated in, we thought about every way, right? So that you can have an Ethernet cable, you can connect it with a hotspot on your phone through then to a network, or it has an integrated wireless LAN adapter in there. But I mean, if the IT at the place where you send it doesn't allow to integrate new devices or so, which are unknown to them, then obviously all that nice solutions do not work, or if there are some restrictions on the name of the wireless LANs, which are then not recognized by the device, and so on. So again, these are very important and often probably not thought about issues which can arise and need to be dealt with. Yes, I think overall, I mean, the most important thing is like, I mean, you don't want to just develop excellent technology, nice devices, beautiful assays, and then have no impact. I think that at the end of the day, that would be not successful in our case. I listed here two different examples. On the left side here, a more positive one where I think where the integration of our technology worked out quite nicely. And on the right side, maybe an example, I would not say a negative one, but maybe one where there is quite some room for improvement. On the positive side, I have here an example of how our technology was used to support the malaria indicator survey on Bioko Island. That's a small island in West Central Africa. And there we used our technology, our PCR technology with very simple and low cost cartridges where we detect just malaria parasites. So no species identification, just any malaria parasite which can infect human beings. We did in this case for quite high throughput. So on one cartridge you could test for up to 18 different samples in a relatively short time, as our technology is fast, and for very low cost per samples. And from the very beginning, that we were included basically in that project, which was run by the National Malaria Control Program. And because there was this nice collaboration, this is actually a project which, or also now also became kind of its own project, which works quite nicely, and our technology can be used every year to test dry blood spots which are collected in the field when they do their annual survey on malaria. And they still do it like besides testing with rapid tests, but it's more and more PCR because it's more sensitive as the tests, and gives a little bit more information than just rapid tests. But eventually there will be a complete switch where the entire indicator survey will be based on PCR. And then maybe on the other side where we faced a little bit more challenges is we worked on a project on early detection of cholera in wastewater, and that was in Zambia. Here we started with a partner here in Switzerland. We used their assays which they developed, which were very nice, and also allowed not only the detection of Vibrio cholera as a bacteria, but also did the genotyping at the same time. And basically the assays are able to distinguish between like normal environmental strains and strains which can cause epidemics. Everything on a single cartridge, but that had actually kind of because of that, it's way more complex. On the cartridge, you don't measure that many samples because you have multiple markers, and the data interpretation is a little bit more complex because now you don't have just a simple answer like on the left side where you have like this sample is infected with malaria parasite, yes or no. Here it's basically, yes, there is Vibrio cholera, but it's not one of the epidemic causing strains, or it's positive for a marker of one epidemic causing strain but not the other, and that obviously is way more complex, and the throughput itself is also slower because you can measure less samples at the same time. And here I think one of probably the biggest mistake was that basically that was developed here, it was tested here, and then was basically just sent there in one of the national labs, and just ask them, I mean, can you please try it? So I think also ownership from like the end user side was probably way lower than on the left side where people were integrated very early on during the development of the technology. One thing which is very important, and it was also briefly mentioned by Michele, This is how can we actually observe whether something is robust or not in the field, on the devices, and that has a lot to do with the controls. And I think this is key to have robust technology. So we integrate. We have several integrations or controls in our platform. So we look at the sample adequacy. We have extraction and process controls, amplification controls, contamination controls. So they are run with every single cartridge. They are monitored by the device, and very important, they're not just monitored, but also the device basically gives then feedback again to the operator if something is not correct, and it will inform an action that can be you have to retest, you have to recollect the sample, for example, or you can completely reject that test because something is off. And here the key is, and it's something we have not really talked about yet, but apart from like the chemistry, which I just showed what we do at Diagso, and the hardware, which we just also were introduced by Michele, we also do software. And I think software here is the really nice link between basically chemistry and then the end user, right? So where you use algorithms to make decisions for the end user. With that, I would come to the end of my presentation. As mentioned, robust molecular workflows, they must tolerate sample, operator, and environmental variability. Otherwise, that will not work. And I think very important, make sure it's well integrated in existing workflows. You can have the best technology if it's not integrated in workflows, and everywhere workflows are existing, they might be better or worse, but they are there, and you need to adapt. Yeah, simplicity is often the strongest design choice. I think that's true. And also, as just shown before, the controls are very important. They are basically in every run you have a set of controls, and you make sure that they are fine. And then also, the earlier you test technology in the field, the better you can adapt, the better you can make it better. Thank you very much. If there are any questions, happy to answer them.
Since Expedite is historically coming from the other end of the diagnostic workflow compared to Diagso, I'm more talking about sample extraction, nucleic acid extraction, more than actual amplification. And most of the work, or the recent work that we did and the developments that we did were happening in the framework of an EU project called Preparedness, where also Diagso is a member of. And within that project, we are looking for developing different tools that should equip the European society mostly with tools for preparing for the next pandemic. That's the big story behind it. And that is essentially 3 different pillars within the project. One is molecular home testing platform. Another one is a multiplex qPCR platform that is also developed and was shown by Michele and Toby in the previous talks. It's coming from Diagso. And the third pillar is a mobile suitcase laboratory, which enables mobile nucleic next-gen sequencing. And on top of all that, the task of Expedite Diagnostic is to provide rapid nucleic acid extraction technology, which that's a particular challenge and requirement, can be applied also outside of established big lab infrastructures. So, and today I'm going to split my time into 2 different topics. One is what we call ultra-rapid virus extraction. That is particularly in the framework of if you imagine an outbreak is happening already, you see many cases coming up. How can you deal with that? Again, from an extraction point of view. So we think we have a nice solution there, and I'm showing you what this is about. And the second half is more looking into something that we have recently developed and are close to launch also, make it available to the public, which goes more into environmental monitoring or epidemiological questions, where we have developed a method for extracting virus particles from large bodies of water, mainly wastewater, and have coupled that with a nice automation solution. So that is the second half of my talk. So the first one, this very rapid extraction of nucleic acids, for that, actually it was the main topic of, I think, the first episode of this Prepare TID webinar series. So those of you who were also attending this might be already a little bit familiar with that. So the system is based on our toolbox that we have within Expedite, and that is the basis of many of our developments. There we utilize a technology that we call reverse purification, which simplifies extraction and cleanup of samples quite a bit compared to conventional methods. And in this, it's essentially a 1 or 2 step process here. The first one is to mix the sample with a lysis buffer, a proteinase, and the magic ingredients, the beads A. And then you apply heat. By that, of course, you inactivate nucleases irreversibly. You also disrupt viral particles, in our case here. And then what happens afterwards is just a magnetic separation, where impurities from the sample, in this case blood plasma and serum, are bound to the surface of these beads A, which are paramagnetic microparticles. So the surface is equipped with a certain binding features that bind to those inhibitory substances present in various biological samples. And by just applying the sample mix, the suspension to a magnetic field, you remove those inhibitors bound to the magnetic beads to the side of the tube. And then what remains is a supernatant that is cleared from many inhibitory substances and can then be directly used for nucleic acid analysis. So the whole process is very short. It's like 6 minutes really, and has obviously a couple of advantages. It's very simple, so it's field applicable with minimal hands-on time. It's almost instrument-free. It includes inactivation of nucleases, but also removal of amplification inhibitors. And very interesting feature that we recently validated is that you can also do this as a sort of batch extraction. So if you think of a 96-well plate PCR cycler, you can actually do this whole extraction process here in the cycler with a temperature setting, and then afterwards take the whole plate out onto a 96 magnet grid and do the magnetic separation. And what you have then after these 7-8 minutes is 96 extractions ready for PCR amplification. On the other hand, this very short and rapid extraction also have a few limitations. One is it's the sample volume that is not as big as if you would do a full like silica column extraction of viral RNA. So there's also no enrichment, no concentration of the viruses from, let's say, 500 microliter sample into 50 microliter eluate. That's not part of this scheme here. And with that comes naturally also a lower analytical sensitivity. The good news, however, is that still, despite of the lower analytical sensitivity, the diagnostic sensitivity is not suffering so much from this. We have performed also within the Prepare TID project clinical validations with the method using various CE-marked PCR kits for detecting different virus species. And this slide is just giving a summary of that. As I said, last year I provided a little more details of the studies, but this year is just a summary. So this study was done in 2 sites in Italy and Turkey, included 175 samples in total. 77 were clinical positive, 66 were clinical negative ones, and we also added 32 spiked samples for some of the viruses where we didn't get hold of naturally clinical positive samples. So you see in the graph here, let me get the pointer. Don't see my mouse. Anyways, so you see the array of viruses was ranging from things like chikungunya and dengue, where we have really upcoming threats, let's say, to southern parts of Europe already, to other viruses like the Crimean Congo hemorrhagic fever virus, which is still a little more of a concern in the Middle East or Turkey region. So we compared this very rapid extraction mechanism. Product is called SwiftX virus with a full-blown silica prep. And the diagnostic sensitivity and specificity data is, you see it here in the table, are quite impressive. We have a 100% diagnostic specificity and quite nice diagnostic sensitivity of 98%. So you see, despite of just using a small volume of sample, you can reach a very high diagnostic accuracy. So to summarize that part, the key takeaways from that rapid extraction is it's essentially one-step protocol which extracts total nucleic acids. So no matter if you have RNA or DNA viruses, both RNA and DNA will be present in the lysate. The extraction time is very short. It's an active removal and cleanup of the samples, which is a big difference to other rapid extraction solutions by other competitors who mainly just have a lysis buffer, sometimes also a protease, but they don't have any means of really actively removing inhibitors from the sample afterwards. You can do this in batch processing, as I explained before. Meanwhile, we have collected evidence on more than 300 clinical samples for the diagnostic validation. And the product is also available as a CE-IVD marked version, which can officially be used for routine diagnostics since, I believe, July last year already. Okay, so with that, I would switch to the other topic, as I introduced, that is more looking into environmental testing. So we have a new kit around the block here, which is a kit that we will call SwiftX wastewater. And the purpose is, as the name says, to extract pathogens from wastewater samples mainly. The capabilities of input volume are 10 to 35, 40 milliliter. And the total processing time of the process, including the concentration from those initial volumes, will be around 90 minutes. It's a 2-step process, which we can perform in an more or less automated fashion in 2 phases. First phase is use this wastewater sample, currently validated as 10 milliliter. Add the capturing buffer and the magnetic particles again, which will then lead to binding of viral particles to these magnetic particles. And then with the automated process, this will be concentrated. The viral particles will be concentrated from the body, the liquid body, and will be lysed in the end of this part of the process, which is then used as an input to a more conventional, also cartropic lysis and purification mechanism based kit for doing a further concentration of the sample and also a complete cleanup so that we remove all the wastewater inherent inhibitors, which are actually quite a hassle. If you really have not worked with wastewater samples before, it's tough. That I have learned it's much more complicated than you would think. So, as I said, the first process is, well, the whole extraction process is intersected in two parts. The first part is dealing with binding viral particles to a magnetic surface, which can then be used to concentrate the particles, the viruses. And for that, we utilize our cell capturing technology, have it adapted to this new objective. And with that, we can very nicely, you will see the data later, very nicely and efficiently harvest, so to say, viral particles in water bodies and concentrate and lyse them in very small volumes. And the second part, as I have explained, is a more conventional extraction method, which we found out is necessary because wastewater samples are so difficult and rich in inhibitors that we decided to go with a very strong and conventional, in this case, purification chemistry. So we have gathered first data. We are also in contact with many wastewater treatment plants here in Germany. And what I like to show you today is first robustness data on virus recovery from wastewater samples. So to give you the specifications, starting volume was 10 milliliter of wastewater. We spiked that with a concentration of 500 particles per milliliter, means 5,000 viral particles in the whole 10 milliliter. And the whole extraction was done in the automated fashion with the instrument that I'm also going to show you later a little bit more. With the chemistry, which I just explained, and the analytical downstream part was performed using a real-time PCR kit, which in this case was a multiplex kit and can detect 3 viral species simultaneously. And that was SARS-CoV-2 virus, RSV-A, and also influenza A. So as you see here, the robustness of the recovered CT value is very nice. You see across, almost 15 different wastewater samples, you see a very narrow range of fluctuation. That is showing you that the recovery is quite consistent throughout all these different wastewater bodies that we used here, which came from different sites within Europe. And the second set of data I'd like to share with you is about the sensitivity. For that, we again use 10 milliliter of wastewater as a starting volume, spiked it with different levels of viruses. Again, these 3 viruses, which I just explained. This time we tested 550 and only 5 viral particles per milliliter. Have gone through the same mechanism in terms of automated extraction, and the eluate that we received in the end, we used to rehydrate the freeze-dried real-time PCR kit or assay. That's actually particularly challenging if you imagine that you don't have just like 5 microliter and a 20 microliter PCR, which is your eluate coming from really dirty wastewater, but it's just the eluate that you use entirely to rehydrate a sample, PCR reagents, and it's still running nicely. We see very robust amplification seen by the internal control signals. And here what you see in this graph is the CT signals of the different virus strains, depending on the viral input. And as you see, it's also, again, quite robust and indeed sensitive. So we can detect up to or down to 5 copies of viral particles per milliliter, which is really, really nice and astonishing, especially if you think that, or if you remember that this is a completely automated process. And this is something that we think is very new to the market as well, to the field of wastewater testing. So this process here is, as I said, automated. has a potential to scale up to 40 milliliter of input volume, also with our automation platform. And with that, would replace methods like filtration or PEG precipitation that are now state-of-the-art in this wastewater testing fields completely. And we see by the data that the removal of these very various and heterogeneous inhibitors in wastewater bodies is very robust. We have validated it with samples across Europe from different European wastewater plants and also various virus families. We even have data beyond these three, what you see here, but I won't share it today. We'll see it later. That is a ready-for-use tool for epidemiological studies, but also for environmental monitoring and testing. And the evaluated nucleic acids that are the output of this extraction workflow are compatible with methods like real-time PCR, but also digital PCR, which is gaining interest in the field due to its supposed to be high inhibitor resistance, as well as absolute quantification, which is clearly an advantage over real-time PCR methods. So what is this nice machine that we have used here for? It's also one of the fruits coming out of this Prepared TID project, which I introduced in the very beginning. It's a small and portable extraction instrument, which is capable of processing samples ranging from, let's say, standard volumes like 200 microliter, which are very typical in the diagnostic field, to up to 40 milliliter, which is more like applicable for things like wastewater testing, but also can be used for urine testing if you think about STDs from urine samples instead of need to rely on swab samples. It has a capability of simultaneously process up to 4 samples. So 1 to 4 is completely up to the user. Also, the plastic use is completely flexible in that respect. It has 2 heating zones. That's more standard. One is for the input material, if necessary. One is for the lysis elution tube. It also includes rotational rod sleeves. That means it can actively mix also large liquid bodies, sorry, like 30, 40 milliliter, easily mix it by rotation, which enables a nice mixing function, of course, but also not to forget the whole operational noise is very, very low compared to other systems where you just have some rod that is dipping in and out as fast as possible into a liquid, which generates a lot of noise. Elution volumes down to 50 microliter. It's a very modern graphical user interface. Is a touchscreen based system. Of course, you don't need a computer to operate this machine. And as I said, its dimensions are really made for portable use. So it's slightly under 15 kilos. Can also be battery operated. So it's really meant to be also used outside of central lab structures. Just 2 more slides, I think. One about the consumables, because we also followed their very different approach and mentality or philosophy. The plastics you use to perform the extraction, for that you can really use standard plastic materials that you can buy from typical plastic suppliers like Sarstedt. And the system is flexible in the very first tube. It either accepts 5 or 50 milliliter tubes, depending on the input volume that you want to process. Then there are a couple of 5 milliliter tubes, and the very end, the elution or lysis tube, is a standard 2 milliliter tube, as you find it in every lab shop. And then, of course, the rod sleeves are something customized to the machine. But the rest you can really source from, as I said, from any plastics supplier out there. Just a few words on the rod sleeves themselves, put some thoughts into it. So it has a groove where it can, where an O-ring can be fixated. This function we don't need for the protocol which I just introduced, the wastewater. But of course, we have a couple of more ideas in mind and different applications, such as, because the question was there in the beginning, solid sample homogenization. So we also have thought about ways to use this extraction machine for really tissue homogenization. And there we will also make use of this O-ring eventually. Another function that we are using right now, due to the need for mixing large liquids, large volumes, is these blades on the outside, which really enhance the mixing of the liquids within the vessel. And this asymmetric structure that we have a very narrow tip, which then can also work nicely with this 2 milliliter tubes geometry that we have in the very end, where we want to elute our nucleic acids in as low as possible volume. And then what I said, this flexible configuration, either you use this adapter or you don't, depends on whether you want to fit 50 milliliter centrifugation tubes into the machine or just 5 milliliter tubes for smaller volumes. So that flexibility is given. And with that, I say thank you for your attention. And of course, happy to take any questions.